Good afternoon and welcome to Learn at Home with BIA. My name is Daniel Wolfsleigel and I am a 6th grade math and science teacher at Lycoming Valley in Williamsport. So today I want to talk to you about a very attractive topic. All day, every day, you're pulled on by something you can't even see. It's a force that lets an outfielder catch a fly ball, and it keeps the moon and the earth going around the sun. I'm talking about gravity. But what exactly is it? And how did it help to shape the planets as we know them?
Some vocabulary to know for this lesson. Mass, the number, density, and type of material in an object. Gravity, the force that attracts one object to another. Solar system, a system of planets or other bodies orbiting a star. An asteroid is a rock in space. A meteor is an asteroid that has entered Earth's atmosphere. A meteorite is a meteor that touches the ground. Interstellar is the space between stars. Kinetic energy is energy from movement.
You see gravity at work every time you drop a book, or step on a scale, or toss something into the air. But even with Newton's story about how an apple fell from a tree, like the one behind me, how well do we really understand gravity? And how is it able to form things like the solar system and entire planets? So what do we know about gravity? We know that it causes any two objects in the universe to be drawn to one another. And we know that gravity helped form the universe, keeps the moon in orbit around the earth in orbit around the sun, and is responsible for the tide when you go to the beach, or even to blame when you fall off your bike. As for the science behind the action, we know that Isaac Newton defined gravity as a force. So that's one that attracts all objects to other objects in a way that we kind of think of like a magnet. Now we know that Albert Einstein had a different theory. So Einstein's theory was that gravity worked more like a wave type on a structure. So it's a result of what he called the curvature of space-time. Now, those two theories are the most common, but they don't really tell us everything that we need to know. So in order for objects to have gravity, they have to have mass. So let's start by trying to explain mass. So one of the effects of mass is that it attracts other things with mass. But what is that?
As molecules move closer together, an object becomes more dense. This creates mass.
Okay, so when we're describing density, and we're trying to figure out what that would be, you could take a couple things right out of your kitchen cabinet. So I'm going to start with some basic jars, and I have a little bit of food coloring. And I have here, you can see, 2 ounces of oil, just regular cooking oil, and 2 ounces of water. Now what I want to show you is that while they're the same amount of liquid, and they kind of behave about the same, they weigh almost the same, one is more dense, and that of course being the oil, and you can see the way it's settled right here. So how can I prove that to you? Well, one thing I'm going to show you, because I tried to get the light in the background here, is I'm going to take a little bit of this food coloring, and I'm going to drop it in here. And hopefully that will help to separate out. Let's mix it around just a little bit. Get a little mix in here. All right, so we have some food color. So now you can see a clear distinction between the two. What I want to do now is separate them to the side and bring in my other jar. All right, so what should happen if density, this being more dense, meaning the molecules are either larger or more close together, or a combination of the two, is that these will separate. So I can go ahead and put some water in, add some oil, and as they're pouring in, you'll probably see some bubbles forming. Now, if I step back and look at them, right, so I have my 2, and I've poured them in, I step back and I look at them, you can see that even though they were about the same amount of liquid, and they were about the same weight, the same volume, the consistency was different. One is more dense than the other, and that separates them. They won't mix together because of the different densities. Pretty cool. Well, I take, for example, this ball. Now, this ball is pretty foamy. So it's light. It doesn't have a whole lot of mass. If I throw it in water, it's going to float. So what we're really talking about is not necessarily the weight of it. Because if I took another object, such as a rock of the same size, most rocks of this size would sink right to the bottom of a lake. And there we're talking about the mass that an object has. We're also talking about how dense it might be. So the more dense something is, not just big, the more mass that it has, and therefore the more gravitational pull it can have. So we think of this in terms of something like a black hole. It doesn't have to be big to have a whole lot of density and pull. So when we're talking about smaller objects, such as your computer, or the desk, or even your house, that's relatively small compared to the universe, they don't have a lot of pull. The force of gravity is very, very tiny. But when you have something that has millions, or billions, or even trillions of tons of mass, the effect that gravity has really starts to pile up in there. So what we are saying is that actually you have gravity. The chair you're sitting in has gravity. The house that you live in has gravity. But it's not enough that we really notice in our day-to-day lives. It's not something that we come across and get sucked against the school bus because the school bus is bigger than us. So in that way, gravity is not really that important. So once you start building and building and building something, say, the size of this planet, then you've really got a mass of an attraction. And all of that mass pulls on other things with mass, and it creates the most efficient shape, a sphere.
What does this tell us? Objects have mass, and mass creates gravity.
For smaller objects in the universe, things like asteroids, the force of gravity trying to pull that object together into a sphere is just not going to be enough. So a lot of our asteroids and things like that are misshapen. They're not spherical. But once you get above a certain mass size, the strength of the object can't stop the force of gravity from pulling it into a sphere. So objects that are larger than about 1,000 kilometers in size are able to pull themselves into a sphere. So 1,000 kilometers in size, it really starts shaping up nicely. In 2006, this caused a lot of controversy when we made being sphere-shaped and having that ability one of the requirements for an object to be considered a planet. So a couple things. They have to orbit the sun, first and foremost. They need to have cleared all the smaller objects in their orbit out of the way. So all of the other asteroids, things like that. Now there could be moons, and they've collected those, but they need to be the dominant force of gravity in their orbit. And they have to have enough gravity on themselves to pull themselves into a sphere. So most of us have now heard that where there used to be 9 planets, poor Pluto was demoted to a dwarf planet, partly because it's just not spherical enough. Okay, so a different way that we could approach the idea of gravity and understanding that it makes a sphere is to realize that if we're blowing bubbles, for example, a bubble automatically becomes a sphere. But why? It doesn't really have any mass inside, so there's no way that gravity is pulling it in like it does the planets. But if we take these bubbles that keep passing by here and we look at what's going on, it's a very similar idea. So instead of the gravity being inside, we have air pressure. And air pressure is built up in the middle and on the outside, and it distributes equally. And that's one of the ways that gravity helps make things into a sphere, right? Because all of the gravity is pushing equally on all directions. So we're going to take our bubbles here, and we realize that this is a big fancy phrase known as hydrostatic equilibrium, which really just means that the gravity and the tension on the surface is able to pull itself into a sphere because all of the pressure is coming at it equally. Now with the bubble that happens outside, but with gravity that happens inside. So in a very similar way, it's a way we could kind of explain how gravity has helped to shape the planets into spheres. Now, it is possible to technically make bubbles that are different shape, but bubbles automatically want to become a sphere.
What this tells us. Gravity, pulling equally on all sides of an object, makes it into a sphere.
Now, there have been several theories about the creation of the solar system, just as there are with the creation of the universe. The favorite idea is that the origin of the solar system begins with a gravitational collapse of part of what's called an interstellar cloud. Now, this is interstellar, so it's something that's literally floating in between the stars. So it's gas and it's dust and all kinds of stuff, right? And so its initial mass was probably only 10 or 20% greater than the sun is now. So these items are floating out there and they're bumping into each other. Somewhere, there's a push in the right direction. Maybe another star exploding and sending a shock wave out into space, like someone dropping a rock into a pond. You can see the waves like that. So you have a group coming together and building mass. And the more mass, the more gravity. The more gravity, the more pull. The top and the bottom begin to collapse in a bit due to gravity. And if it's a galaxy or a solar system, it'll begin to flatten. So let's take a look at a beginning solar system. Now, this structure is commonly called a solar nebula. Now, it resembles the shape of a typical spiral galaxy on a much reduced scale, very, very small. So now, as gas and dust start collapsing towards the center, there's potential energy that becomes kinetic energy. Now, kinetic means movement, so it's the energy of motion. And as movement increases, the temperature of the material rises. It gets hotter and hotter and hotter. And eventually, the temperature becomes so great in the center that a nuclear reaction begins. And that is how a sun is born. Now, a collapsing cloud region quickly becomes roughly spherical in shape. And that's because it's revolving around the center of a galaxy. Now, the farther the material is away from the center, the slower it moves, which causes the whole thing to start collapsing. So think of water going down the drain. As you're watching something approach that vortex or swirl that's in the center of the drain, now it's moving slowly, but as it gets closer to going down the drain, it moves faster and faster and faster. And because of this, the cloud begins to collapse in on itself and become a sphere. Now it starts to rotate to conserve something called angular momentum. Its speed of rotation gets faster and faster and faster as it comes together. So you can think of this sort of like a figure skater spinning on the ice. The closer their body gets to itself, the faster they spin. So you can kind of think of this as the more spread out something is, the harder it is to turn. So in order to conserve that energy, it gets tighter and tighter and tighter. Okay, so when we're talking about the spinning, we have an example here that most people are familiar with. It's a top. So I can take this top and I insert this strip right in here, and that's just going to spin the center, causing this particular object to spin around and around and around, and then it will start to pull itself, or most of its force, towards the center and keep it going flat. Now, if I were just to hold this up and try to spin it clumsily with my fingers, it doesn't do very well. I mean, it might, if I get the right amount of push, I could get it to spin pretty easily. This particular top has a center structure in it that equally balances the weight as it spins, much like our figure skater, right? So if I take this and I'm going to insert this strip right here, and now this part here is going to pull and make the inside spin. Let's see if you can see that. Make the inside spin, and we can see something very cool. So it'll spin around much like our figure skater did. When I take it and I pull the center, you can see that it spins, showing us that conservation.
What this tells us: objects in space spin to conserve momentum.
Now, it may seem that space is this big empty place, and there's not really much going on, but really, there's a lot. So what you end up with are objects that are getting pelted from all sides by objects going really, really fast. And they can sometimes go as fast as 17,000 miles an hour. This is incredible. So as these objects are hitting, they start gobbling some of them up. and collecting them. And that adds to the mass that they have, which in turn creates more and more gravity.
What this tells us: the more mass something has, the more gravity it creates. So, the experiment that we're working today, we're taking a very basic concept of using what we have, and we have a glass container, and we have some just regular dollar store saran wrap. So we're going to take our dollar store saran wrap, and when I introduce something like a steel ball. So this steel ball, as you can see, when I place it on the saran wrap, it tends to push down a little bit here towards the center. So you can see that's just a little bit lower than everything else. Now, what happens if I introduce another ball over here? Well, over time, I can get them really to kind of stay separate. But the more weight that happens, they start pulling towards each other. So as I add more weight, everything tends to be drawn towards that central mass. And you can see it's dipping down. So if I took all of those at once and separated them out and released them, they would all start pulling together pretty quickly.
So if we take Einstein's idea that gravity works as a distortion of space-time, in fact, he called this the fourth dimension. So the first three being height and width and depth, and then gravity, because it distorts time. Now, if time and space work like this trampoline, the smaller items will change it just a little bit. This is like our everyday items, right? Our small asteroids, things like that, our house. However, if I get on here, we have considerable mass, and you can see that I have a much larger impact on the space-time around me.
And now, we take a little break with random trivia. Shake off the nerves and get the blood pumped into your brain. Grab a friend, because it's time to go. Okay, so for today's trivia, I really kind of had to stop and think about what I wanted to do. I mean, space is so cool. It has so many interesting facts to really focus on. But then I got thinking, what's something that would absolutely blow your mind? How about some volcanoes? So, the question today, which of these planets is home to the largest volcano? Think about it. Do you have a guess? Let's find out. Let's go over your choices, shall we? We have A, Pluto, B, Earth, C, Venus, D, Mars, or E, Neptune. Take a minute and think about it. What are some things you know about these planets? Any ideas? Let's find out. First up is Venus. Now, Venus is almost as big as Earth, and it's often been called Earth's sister planet. At one point, it was thought to be a tropical paradise, although not anymore. You see, Venus happens to be the hottest planet. It can get over 860 degrees Fahrenheit or 462 degrees Celsius on the surface. That's hot enough to melt metal. While Venus does have a huge amount of volcanoes, and in fact, no one's counted them all, but it could be as many as 1 million. There's not a lot of exploding volcanic activity. It's mostly just lava flowing out. And also, not home to the biggest volcano. Sorry, Venus. Next up, Earth. This is my all-time favorite planet, because it's where I keep all my favorite stuff, like family. Anyway, Earth has a ton of volcanoes. Now, most of them occur near what's called tectonic plates, and these are pieces that separate the crust from the magma underneath. Most of these occur in what's called the Pacific Ring of Fire. This is an area around the Pacific Ocean where over 75% of volcanoes on Earth are found. Now, we do have some very famous volcanoes such as Mount St. Helens, and we have some big volcanoes, but unfortunately, not the largest. Sorry, Earth. You know I still love you. Anyway, let's see what's next. Pluto. Ooh, when you want to talk about cold. So, water freezes at 32 degrees Fahrenheit. Well, the average surface temperature on Pluto is negative 380 degrees Fahrenheit. It is so cold that some people think Pluto actually is home to ice volcanoes. Yeah, I don't really get it either. While Pluto is only about 80% the diameter of the moon, there's really nothing big about Pluto. Definitely not home to the largest volcano. Next to last, Neptune. All right, let's show us what you got. Now, there's a lot of really cool things about Neptune, but what Neptune is most famous for is its winds. Neptune's Great Dark Spot has been clocked at almost 1,200 miles per hour. That's an insane amount of speed. That's way faster than any of our hurricanes, but it's also made of gas and therefore would be impossible to have a volcano. Well, with all other contenders out, that leaves us with Mars. Mars has one of the solar system's most famous volcanoes. It's called Olympus Mons. It is so big. It is 13.6 miles tall. 13.6 miles tall. That is over twice as high as Mount Everest. It's so big, it's approximately the same diameter as the entire state of Arizona. Absolutely massive. Let's give it up for Mars and Olympus Mons. You are the largest volcano in the solar system. And now, let's go back to the show.
Hey guys, you're probably wondering what I'm doing out here. My sweatshirt on a chilly night. Well, I'm looking for shooting stars. I'm really hoping I can get that wish, seeing that rare shooting star come across the sky. Man. Well, actually, I know it's not that rare. It's not a star. It's a meteor. Small pieces of rock called asteroids, right? They come near to Earth all the time. Gravity brings them in. So most of the time, they burn up in the sky as they're going overhead. See, there's friction created when they enter Earth's atmosphere at such a high speed that it actually creates a fireball of rock. And that's what we see streaming across the sky. Usually, they burn up in the night sky. Most never actually come and touch down here on Earth. That's actually, that is pretty rare. But we call them meteors or shooting stars. They're actually just balls of rock from space burning up in our atmosphere. Now, they are beautiful to watch, but most of the time they're not really harmful. Now, they're not rare either. See, they're just rare to where you are. So according to the Planetary Science Institute, as many as 500 meteorites hit the surface of Earth each year. Now, most of them are not large, so they don't create much of an impact, but on average, 500 objects from space coming to touch down on Earth is pretty significant. And that's not even accounting for most of them that burn up in the nighttime sky. Really want to see some shooting stars. You can track meteor showers online and get a really good chance of seeing one. But randomly looking at the part of the night sky where a rock hurtling through space has been pulled into the Earth's atmosphere by its gravitational effect or its mass and therefore burns up in a nighttime display, where I just happen to be looking at that point, it's pretty rare. Maybe I'm not getting that wish tonight after all. So what did we learn? Objects have mass, and mass creates gravitational pull. And as objects get pulled together in space, they spin to conserve momentum. Eventually, you end up with a system of large mass objects spinning or rotating and orbiting around each other. And this is how a solar system is formed. Well, thanks to that invisible force that keeps us from floating off the planet, gravity. I'm Daniel Wolfsleigel, and thank you for discovering with me just how gravity created solar systems. And thank you for joining me on Learn at Home with DIA.